Okay, so let's begin, guys. So the first thing that I want to show you here is that on Iconestoga, okay, so when you get into your content, I want you please to do the following. Like after this class today, on the content, I want you please to go into the SCR, which is the topic, the very last topic. And there you are going to find like a very lengthy document explaining the SCR. And we don't have time in 1 hour to go through this document. However, it's just give you some basic information, some additional information in case you want to get more from the SCR, in case you want to get like a more in-depth study about the SCR. So I'm just making this available in case that's your choice, in case that's what you want to do going forward. Okay. So it show you like how the SCRs look like. It show you like the symbol for the SCR and how is it built being a PN junction, okay? And other than that, we just give you a bunch of information and it shows you like all the different type of configurations that you are going to find out there in the field for SCRs. So this is just a lot of information about the SCR that within 1 hour, we don't have enough time to cover. In anyways, this is just good reading material. So there's not much that we can cover together. If you happen to have any questions once you read it, then I will appreciate that you either send me an email, and it's even better if you keep your questions so you can show me when we gather together in the shop. Okay, so anyways, in spite of that, there is a PowerPoint presentation, which is the PowerPoint presentation that we would usually use in order to do the SCR. So you can see here that in this presentation, some of the stuff that is discussed is like the operation of an SCR in a DC circuit. And we are going to discuss this today, but we are going to do some calculations at the same time. Also the SCR in an AC circuit. Also, like we are going to see like the schematic symbol. And of course, we are going to, well, we are not going to discuss it in this class right now, but you are going to be able to see it on the PowerPoint that using a capacitor and shifting the time of when the SCR fires, you can phase shift the SCR and gain full control of the output voltage. So anyways, guys, so I'm just gonna be leaving this PowerPoint for you to review because that's going to be another important aspect that you can review, but we don't have enough time to cover that in this class either, okay? Because I want to concentrate on the most important practical aspects of the SCR. In spite of that, I also want you to be able to watch two small videos. The first video is about 1 minute, and it shows you like when you click on it, it's going to show you how the SCR works, like in a circuit. And that video is only like 1 minute. And the other video is more professional, is lengthier, and it's going to show you like how the SCR is built and how is it that it can be used for high power DC transmission. High power DC transmission is the most effective way to transmit high power, from very long locations. And you may wonder, oh, I thought it was AC. And I thought that was because of the ability of being able to transfer AC over long distances. I thought that that was why Nikola Tesla won against Edison. And that is true, that was true until the SCR came along. So the SCR has made possible high power transmission in a very efficient manner. So a lot of hydro stations, they use SCR and they convert your AC power into DC in order to be able to transmit it over very long distances. But this is not the point of discussion today. I just want you to be aware And this is going to be discussed in this video, that's one of the advantages of using SCR in circuits, okay? Okay, so something else that I want you to be able to do as well is that once you go through all these different videos and also PowerPoint, I want you please to take a look at this circuit, okay, which is an SCR in a DC circuit. And also there's going to be another simulation that I have done for you. And these are the simulations that you will actually do in the shop of an SCR being used for phase shifting. And by controlling the resistance, I am able to control, okay, by controlling like my variable resistor right here, I am able to control my output voltage on the SCR. Like both in AC and DC, we are going to have the same instance, the same result. However, you know, this demonstration, these simulations has been made available to you just for, you know, just to give you the background knowledge, just to start giving you what is it that you are going to be facing when you do your lab. Okay, so today we are going to get started. I mean, that's what we are going to be doing with the SCR. Okay, now on the other hand, I also want you, okay, to go back, and we'll do this first today. I will also go back to the Zener diode, and I think I already gave you like the idea about the Zener diode. I already gave you like some of questions in the actual test, but I don't remember if you have done your Zener diode lab yet. I don't think so. Have you? Any comments? Nate, you always talk. Can you talk, please? Have you done your Zener diode yet? Oh, you did. Perfect. Okay, perfect. I'm not picking up on you, okay? It's just that I remember your name. Okay, perfect. So if some of you have done the Zener diode, that's great. So first, I was giving you like a lengthy introduction on what is it that I want you to do with the SCR. In today's class, the first thing that I want to give you like is the little simulation that uses, okay, so just give me 1 second here. A little simulation that uses like the Zener diode, and this simulation is multisim. Okay, so, and this is something that you haven't done yet. It's something that you are going to be doing in the shop anyways. And in this instance, we are going to explore what is it that happens, okay, through a load when our Zener diode is in line. Something that I want you to notice here is the following. I want you to notice that in our Zener diode, we have on this side, we have that is connected to the ground, a positive terminal, which is called the anode. And on the other side, we have our negative terminal. Now, I want you to notice that the negative terminal of the Zener diode through the switch would be connected to the positive terminal of the power source of my battery. Okay, so you see that the positive stem is connected through the load, through the resistor, through the source resistor, ERS, is connected in parallel with the power source, and is connected not only in parallel, but in a reverse biased fashion, okay, to the power source. And the reason why it's connected like that is because the Zener diode will not work until our Zener voltage has been reached. Once the Zener voltage has been reached, then the Zener diode is going to kick in, and because it's connected in parallel with our load, and there's a rule that says that in parallel circuits, all branches along a parallel circuit are going to have the same voltage, because of that rule. That's more than a rule, that's kind of a law, okay? Because that's always happened to be true. Anything which is connected in parallel, any loads which are connected in parallel will always have the same voltage. So in the case of the Zener diode, because it's connected in parallel with the load right here, that whatever voltage, whatever Zener voltage that we have on the Zener diode will also be the voltage that we are going to have right at the load, which is connected in parallel with the Zener diode. Okay, so now under normal circumstances, I want you to look at what's going to be the voltage that we have through our load. In this instance, without the Zener diode connected, you can see that the switch is open here. We are going to have just a simple series circuit. So in this case, whenever, okay, I can manipulate this voltage here. Okay, let me do it once more. So I can use this slider and I can increase my voltage. I want you to see what happens as I start to increase my voltage. Immediately you see that when the voltage goes up, also the total current through the circuit is going to go up. Also, you are going to be able to see here that your voltage is going to split out between our ERS, which is our source resistor, and our load resistor. If I were to increase my voltage all the way up to 10 volts, then you can see by all means that, well, actually the current is going to be the same on RS and also on RL. You can see here that this current on this ammeter, it is just exactly the same as the current for this other ammeter because we have a simple series circuit. In this case, because this resistor, which is my load resistor, has 470 ohms, that resistor has a higher voltage drop. Like in this instance, the voltage drop here would be 7.58 volts. And if I wanted to determine the voltage drop through this resistor, all I have to do is just multiply my 150 times my 16.129 milliamps. And that would give you a voltage which is going to be equal, okay, like when added to the 7.5, which is going to be equal to the source voltage. Okay, so I'm getting a question here. Oh, perfect. So that would be 2.4 volts. Beautiful. So it would be like 2.4 and a little bit more than just 2.4 because these two voltages add up to 10 volts. Exactly. Always. Okay. So thank you so much, Nate, for the answer, though. So let's keep moving. Now that you can see, okay, I want you to pay close attention to what happens when I close my switch here. Now that you can see that we have the same current right here and here, I want you to focus on 2 points. Number one, I want you to see what's going to happen. I want you to see the difference that is going to happen between this ammeter to this ammeter. And also, I want you to notice that this voltage is going to be crimped, okay? Or it's going to be like chopped down to our 6.2 volts because our Zener voltage is 6.2 volts. And because this Zener diode is connected in parallel with the load, because of that, if my Zener voltage is only 6.2 volts, as soon as the Zener diode get that limit of the 6.2 volts, it's gonna behave as a closed switch, and whatever like additional current that will flow through the circuit based on the increased voltage that we have because of the fluctuation in voltage that we have is going to go through the actual Zener diode. So let's close this switch now and see what happens, okay? I wish I could do this in a slow motion, but I don't have the possibility. But as soon as I close my switch, you can see that actually now still we have our 10 volts and we get here now like 13.70 milliamps. So this 13.71 milliamps plus the amount of milliamps that we have through the Zener diode, it is equal to the total current that flows through my source resistor. Okay, and again, that's one of the rules for parallel circuits, that the sum of all the currents on the branches of parallel circuits is going to be equal to the total current that we have in the circuit. Okay, any questions so far? So you were able to see that even when I increased my voltage, that on the source, you were able to see that by all means, the voltage right here through the load, because it's connected in parallel with the Zener diode, remains the same. If I were going to increase my voltage slightly, you know, just a little bit more, I'm just gonna put it to 15 volts. Now that I have 15 volts, you can see that still we have the same voltage here. Okay, so even when we increase dramatically the voltage, 5 volts is a lot when we are talking about milliamps and all that stuff. The rest of the current, the additional current that is supposed to flow through the circuit because of the increased voltage, when voltage goes up, currents goes up, Ohm's law is not violated by this circuit. So the additional current, because of the increased voltage, is going to flow through the Zener diode. And because the Zener diode only needs 6.2 volts to start conducting or to start behaving as a closed switch, any additional current will flow through it without increasing its voltage. Okay, and that is what causes your Zener diode to have like a fixed voltage, and that's what causes your load to be able to accomplish that state where the voltage remains constant regardless of the input voltage variation. And that's why the Zener diodes are used as voltage regulators. Any questions so far, guys? So, okay, guys, so if you don't have any questions, then I'm going to be leaving this topic for now. And what I want you to do and what I want you to concentrate upon is that I want you, please, if you want, okay, just to go back to the simulations and just take a look at it, you know, take a look at the simulation so you can have like a clear idea on how is it that the Zener diode works in case you are still confused about it. So now let's jump into our next topic, which is the SCR. So in order to do the SCR, what I'm going to do is that, well, let's get started by doing the following. Let's get started by having a background information, the different components that have a symbol which is very similar to the SCR. Okay, so what I'm doing next, okay. So what I want you to see next, guys, is that we have this symbol, and I want you to help me here. Okay, I'm gonna draw a few symbols. Well, my tablet seems to be lagging a little bit. Either it's getting hot or it's getting slow. So if my tablet disconnects, hopefully that doesn't happen this time. then, okay, perfect. It seems that it's gonna work. Good. So here we have a few different symbols that I just draw. So let's begin to discuss some of these symbols, okay? So the first symbol, and I'm just gonna give you time to tell me either to say it out loud or just to type it. So the first symbol that we have right here on the top, can you, okay, so somebody already sent me, wow, that was, that was cool. So someone told me it's diode, LED, phototransistors, Zener diode, and SCR. Perfect. So that's what we have. So we have here the diode. Here we have the LED, the light emitting diode. Here we have the photodiode. Here we have the Zener diode. And yes, indeed, here we have the SCR. So you can see that in all cases, we have two pins or two LEDs for each one of these components, okay? However, like in the case of the SCR, we have three pins. So the SCR in reality looks like a transistor, but it is a diode. So in this instance, we still have a positive and negative, and it's going to behave like if you were going to connect it to an AC circuit, it's going to behave just like a regular diode. And it would rectify your AC into DC voltage, okay? The only difference between this SCR and this diode, they still do the same thing, but this one cannot be controlled, okay? While the SCR can be controlled through a new pin that has been added, which is called the gate. So through the gates, once you have the right gate current, then you can control when is it that the SCR fires and when is it okay, so let me tell you this. So, but once the SCR fires, it's going to remain on until the holding current, okay, so holding current falls below its holding value. Now, next what I want to show you is this little amazing device working in a circuit. Okay, so let's see that. As I said before, there's a simulation here. Okay. So on this simulation, we have our oscilloscope. I'm gonna bring my oscilloscope a little bit lower here so you can see like what's happening. I'm gonna leave my oscilloscope right there so you can see what's happening, okay? So right now, our circuit is off, okay? With the circuit off, that's why that all these yellow dots that represent the current indicates that everything is off. Now, when this is a push button, as soon as I click on my push button, then the yellow dots start to move. And that's when this LED is going to be on. So right now, the SCR, it is working in a DC circuit, and it will remain on until I increase on this slider, until I increase the resistance in my circuit. Once I increase the resistance, which is connected in series with my load, when I increase that resistance, I want you to see what's happening to the animation of the current, which is flowing around this closed loop. Okay, so as soon as I start to increase my resistance, you can see that, yes, indeed, the voltage, okay, when this resistance goes up, the voltage starts to go down, and also the current, until we get to that point. Okay, I'm going to stop the simulation there. Until we get to that point where the SCR just go completely off. Okay, like if you notice here, I'm going to make it a little bit bigger so you can see it better. The SCR was on up until this point, okay? That was like on the 3.4 volts mark. and that was the 5 milliamp mark, the SCR went off. So in the case of this simulated SCR, it have a holding current, which is above 5 milliamps. As soon as it reaches a current which is below the 5 milliamps, it's gonna turn off, okay? And well, if I wanna turn it back home, I have to reduce my resistance back to pretty much to a low value. And then I have to re-trigger, okay, so I'm gonna say this again. I have to trigger my SCR once more. To trigger means this, to turn it on. So I'm gonna run the simulation, of course, because otherwise it won't work. So look at what happened, guys, when I close this push button. Look at what happens here to on the oscilloscope, okay? So look at that. Isn't that amazing? That was dramatic, like a dramatic increase. And once more, so you can see it once more. As soon as I increase my resistance, I decrease. And I'm going to stop the simulation. I'm going to decrease the amount of current that is flowing through my load, which in this case happens to be an LED, until I can shut down the SCR. And that's why you have a sharp decrease. Okay, it's not even a curve. It's just a sharp decrease to zero, meaning that the SCR went off as soon as the holding current went below its holding current value. Okay, so how do you turn on an SCR? In short, you trigger the gate. How do you turn off an SCR? You decrease the holding current, and that's it. Any questions? I hope that you take a chance and that you can play with this. Beautiful, Nate. Nate says that it's like a relay, and that is completely true. It's going to be just behaving as a relay with the advantage that a relay is mechanical. It is an electromechanical device. And how fast can you turn on and off a relay, right? Just a few times a second. While in the case of the SCR, it can be turned on and off thousands of times per second, which is a great, great advantage. But thank you so much for the comment. So let's get moving. So what I want to show you next then, we're going to be getting into a small calculation, and I'm going to be asking for your participation in order to go ahead with these guys, okay? So let's just keep going. In this instance, what I'm going to do, I'm going to draw a series circuit that I'm going to use to simulate a dimmer. So in this instance, I'm going to use this variable resistor, okay? And I'm going to use a light bulb that is rated for 60 watts. Now, my input voltage is going to be 120 volts. And so far, my variable resistor rating is equal to 0-100 ohms. Okay, so far, what I want you to be able to tell me, what I want you to be able to calculate and tell me will be the IL. IL means, if you want, I light or I load. Doesn't matter to me how you want to call this subscript. And also, I want you to tell me, please, your RL. Okay, so using Ohm's law, I want you to go ahead and find out that information. So I'll give you a few seconds to go ahead and do it. Perfect. Somebody already answered like that we are going to have IEL being zero point 0.5 amps, or we could say 500 milliamps, while RL is equal to how many ohms? I'm still waiting. Perfect. Thank you so much. So we have 200. Thank you, Mr. Deliberali. 240 ohms. Perfect. So something that I want you to keep in mind going forward is that this value that we are using, the 240 ohms, is going to be a rated resistance value. That value won't change even if we change the voltage and the current that we have on this light bulb. So just, at the end, we are going to say, remember that I told you at the beginning that this variable resistor was at its minimum value, right at the beginning was at 0. So my voltage here, EL, it is equal to 120 volts. So far, so good. I'm going to erase the 500 milliamps for the sake of a space. I just wanted you to be aware of that. So I'm going to use a different color, and now I'm going to ask you a question. Now, we want to be able to dim the brightness of this light bulb from 60 watts to half its wattage, to only 30 watts. Okay, in order to accomplish that, we'll have to reduce our voltage. And when we decrease the voltage because of Ohm's law, when voltage goes down, our current will go down. Okay, so if I want to decrease this to 30 watts, I want to know at this point in time what's going to be my new voltage and what's going to be my new current. Remember, this value will still remain the same, 240 ohms. Now, in order to be able to reduce this voltage, this resistor that is connected in series with my light bulb will have to be increased in its resistance value. So I want to know how much did I increase these two? Did I increase this rheostat to? Okay, and also I want to know how much it would be my I'm gonna call it source, okay? IS, RS, and how much it would be my voltage here, ES, and I'm gonna call this PS, okay? So in order to do that calculation, I'm just gonna give you another formula to make your life a little bit easier, okay? Just keep in mind that power also, it is equal to E squared divided by R. Also keep in mind that there is another formula that says that power is equal to I squared R, okay? And then we have the regular power formula that says that power is equal to E times I. So I'm just giving you like the other three power formulas for you, just to make it easier for you to transpose and to be able to find all these other values. So I'll give you like, how long should I give you guys? Like, I'm gonna give you 3 minutes to come up with these answers. If I explain it to you, I mean, it would be easy, but sometimes I wonder what would be the benefit, like if I tell you everything. So go ahead, it's all yours. Find the values for these three, like these four values, in this series circuit? So go ahead, please. 3 minutes have gone by. So do you have an answer for me? I am expecting your answers. Okay, perfect. So something that I told you about, thank you so much for the answers. So just so we are clear, something that I told you about, guys, and I am glad to see that a few of you did it, is that this value doesn't change, right? Because this is the load value, and the load value on this light bulb doesn't change. That is an actual physical property. It's an electrical property, but at the same time, it is a physical property of this load, the 240 ohms. Okay, so the value that we wanted to manipulate was the watts, and in order to be able to obtain 30 watts, someone already answered that we would need, and we will round it up just for simplicity's sake, we would need to have a voltage here equal to 85 volts, and that is completely true, is 84.8. So I'm just gonna round it up to 85 volts, which would give us a current. Okay, we would do like our 85 volts divided by our 240 ohm resistor. Okay, because this is 240 ohms. So 85 volts divided by 240 ohms, 85 volts here, right at the bottom there, divided by my 240 ohms would give us how much current? It would give us a current which is equal to 0.35 amps. Is that clear, or is there any confusion on how I did that calculation? Okay, so now that that is clear, remember that this is a series circuit, and in a series circuit, we have something which is called a closed loop. And by all means, on this closed loop, if we have 0.35 amps right here on this light bulb, because this variable resistor is connected in series with the light bulb, this variable resistor has 0.35 amps as well. That's one of the rules for series circuits. Now that we know that we have 0.35 amps, at least we have one of the values. Another rule that we know about series circuits is that the sum of this voltage plus this voltage has to be equal to the source voltage. Because of that, if I take 120, okay, if I want to find this voltage here, ES, I can say that ES is equal to the source voltage, which is 120, minus the voltage here, which is 85 volts. So 120 minus 85 volts, that would be equal to 35 volts that we have right here. Okay, so that's going to be the voltage drop that I have on this rheostat or potentiometer. Now, from that point of view, I mean, having those values, now we can calculate our S, which is the resistive value to which we have to increase our variable resistor in order to accomplish this 85 volt drop. Okay, so in that instance, let's use Ohm's law once more. I'm gonna delete these values here. Oops. Okay. So now I'm gonna use Ohm's law once more because we have voltage and we have current. So my voltage is 35 volts. My current is 0.35 amps. So that means what? That I can find my resistance, which is that value. So I take my 35 volts and divide it by my 0.35 okay? And that would be equal to what? Is that correct? That would be equal to 100 ohms. Okay, so now the last part. Let's determine power. E is equal to my 35 volts, and I multiply by my 0.35 amps. That would be equal to 12.25 watts. Okay, so that's it, guys. So the question that I have for you, okay, I want you please to review this calculation in case I made any mistakes. And now this is the question that I have for you. The question that I have for you is, and something that I want you to notice, is that this here, 12.25 watts that we have on this variable resistor, what is it being used for? Is there any use to that? Perfect. It's going to be producing heat. So all in all, you know what that is called? It is power lost. It is just a loss in power that we accomplish on this city circuit that doesn't give us any benefit. We got to pay for that power regardless. In a very small scale circuit like this, it's not a big deal to lose 12 watts. But if we were going to use like very large amount of power and we have to lose like kilowatts, then we would be very, very concerned. Okay. And that's where the beauty of the SCR comes into play. So now, having this circuit in mind, I'm going to show you how we can substitute in the circuit this variable resistor by an SCR, and instead of losing all this power, then we pretty much can control the voltage here without losing any power. So in order to accomplish that, in order to do that, what we are going to do now is that we are going to draw a circuit, but now I'm going to use AC, okay? So with my SCR, I'm going to install a small variable resistor right there. Okay, and then here I'm going to have my load, which is my light bulb. So what's going to happen now? Okay, I'm going a little bit too fast. Perfect, that's better. So what is going to happen now is that indeed on the SCR, we are going to have an AC input. Okay, still this is the anode and cathode. And this other pin here is called the gate. And on the output, we are going to have DC power. I'm going to draw right beside here what's going to happen when the SCR is triggered at first. When the resistance on this load is 0 ohms. Okay, so we are going to have, like in this case, a full wave. Okay, just for simplicity's sake, we are going to say this full wave is equal to 120 volts. Now, as soon as we start to increase, okay, something else, I'm just going to draw something else here because that's going to be part. I will have to connect the capacitor here, but that's fine. I don't want you to get hung up with the capacitor for now. Just to make things right, okay? So now, as soon as I start to increase my resistance value, okay, Then I start to allow the SCR, I start to control when the SCR fires. By doing that, what I accomplish is that before I used to have like the full wave. Okay, you can see that it's only half a wave, but I used to have my full voltage, all the way with my full max, and all the way like from 0 to 180 degrees. However, as soon as I start to control, as soon as I start to increase my resistance here, because the gate uses a very small trigger current, I'm going to be able to control when the SCR turns on. So if I wanted to reduce this 120 volts to only 85 volts, by controlling this variable resistor, I would be able to cause the SCR to fire instead of here, okay? I would be able to make it fire later on. So I would be able to do this, to have that silent period, and suddenly the SCR turns on, and then it completes its cycle. So you can see here, like in this case, in this instant, that when I used to have 120 volts, my SCR was turning on right at this point here, okay? However, when I increase the resistance and I tell the SCR to start the firing sequence later on in the cycle, then I can shut down or shut off part of my cycle, thus reducing my average voltage, my average output voltage to a lower voltage, okay? And actually you are gonna be able to see this on the oscilloscope when you do this lab. And the beauty of this is that I was able to control my output voltage without power lost. And that's the beauty of this circuit, okay? So I was able to use a very small pot compared to a rheostat that I had to use before. And I was able to use a very small pot to control a large current, a large load, and at the same time, I was able to control the voltage on that load using a very small pot. And later on, when you go to level 3 and you see how DC drive and AC drive work, it's going to be beautiful just to be able to control large motors, large horsepower motors with just a tiny small pot. And all this beauty happens because of the SCR. Any questions, guys? Okay, so this is the class for today, and I hope to see you soon in our next lab. In our next lab, like, do you remember when